In this video, we're going to do a brief review of Chapter 6, and we're going to do a couple practice problems. So the main challenge in this chapter is distinguishing between a reaction mechanism proceeding via an SN2 mechanism or an SN1 mechanism. So let's compare and contrast SN1 and SN2. Let's draw a little chart here. So both of these require good nucleophiles. Where SN2 is usually anionic nucleophiles, and SN1 is anionic or neutral nucleophiles, just by the nature of how this reaction proceeds. We saw at the substitution at the center of attack that SN2 mechanisms are going to be methyl, primary, or secondary. And then SN1 mechanisms can be secondary or tertiary. And for secondary, on both of these, we're really going to look at solvent and determine whether solvent will prefer an SN1 or an SN2 mechanism. Both of these prefer a good leaving group. And in terms of solvent, SN1 is going to prefer polar protic solvents, and SN2 will prefer polar aprotic solvents. So, that being said, just to review, SN1 can use anionic or neutral nucleophiles. SN2 is usually an anionic nucleophile, though sometimes it can be neutral. SN1 is going to prefer secondary and tertiary, and SN2 is going to prefer methyl, primary, or secondary, and secondary really is determined by solvent. You will get the same product, but it'll determine stereochemistry or some of the mechanistic effects. Both of them need a good leaving group. And then the difference in solvent choice, SN1 prefers a polar protic solvent, and SN2 prefers a polar aprotic solvent. So this can dictate both stereochem and reactivity or kinetics. So let's look at a couple examples, and we're going to indicate the products and whether it's SN1 or SN2. So let's draw a couple out here. So we have this alkyl bromide, and we're adding NaN3 in acetone. Okay, that's one. Then we have this alkyl chloride, and we add ethanol, and that's both the solvent and the nucleophile. And then finally we have this disubstitute bromochloro, and we add one equivalent of KCN, meaning there's only one CN, and that's going to be in DMSO. So if you want, you can pause the video here and work on these problems, and then unpause the video and we will go through the explanations of these. So, explaining these reactions, let's first draw the products. So, NaN3 and acetone, NaN3, we have a good nucleophile. So good nucleophile, so that's okay for both of these. We notice we have a secondary center, so that means that it's going to be SN1 or SN2. And then remember, to determine between SN1 and SN2, if it's secondary, we will look at the solvent. Our solvent here is acetone, which is polar aprotic. So it's probably going to be an SN2 mechanism. SN2 mechanisms, we will have the same carbon chain. Remember, SN2 mechanisms are going to do backside attack and invert the stereochemistry. So we had our Br facing towards us, so we're going to have our azide, our N3, facing away from us. Because we had an SN2 mechanism, we'll have it facing away from us. We had backside attack and inversion of stereochemistry. Now for this one, we have a primary center, so that is preferring SN2. And we have a neutral nucleophile, that's okay. We can do, while SN2 prefers anionic, it can do neutral nucleophiles. We have a good leaving group, so we are primed for SN2, an SN2 reaction. Our nucleophile here is ETO. We'll be substituting ETO for Cl. So what we do is we have the same carbon chain, and then where the Cl was, we'll have OET. and we'll generate HCl as a byproduct of this reaction. In this case, in this top one, we generate NaBr as a side product of this reaction. Now, in this case, in this last one, we have two leaving groups that are possible, Cl and Br, and we have Cn, which is a good nucleophile. These are both primary, so we're already preferring SN2, and we confirm by seeing that we have DMSO, which is a polar aprotic solvent. So we are almost guaranteed to do an SN2 mechanism, but we have a choice here. Is our Cl going to leave? Is it going to substitute at the Cl side, or is it going to substitute at the Br side? And looking back at the previous video, we see that Br is a better leaving group. It is it's going to prefer to leave over chloride. So we're going to get substitution at this position, not this position. So we'll keep the Cl and we'll substitute the Br for the Cn because Br is a better leaving group. So this would be a product, and it would be an SN2 mechanism. Note we have substitution at the bromide side, not at the chloride side, so we do retain the chloride. One equivalent means that we only had one CN that attacks. Now, if we had two equivalent, we would have substitution at both sides because both sides are equally good, are good leaving groups. But with one equivalent, we have to choose one, and we have to choose the bromide in this case. Now let's look at a couple more examples and work through them as we did the first one. So here's one. So we have a Cl here, and we're going to add H2O to this. We then have this structure here, where we have this kind of alkyl bromide, and we're adding this structure. This is acetic acid, and that's in ethanol. And then we have this structure, which we already saw, this alkyl bromide. We add NaN3, but this time the solvent is methanol. So if you want to pause here and try these problems out, and then unpause, and we'll discuss these problems as they occur. So again, we're looking for the product and whether it was an SN2 or an SN1 mechanism. Okay, so examining these problems, let's look at this first one. So we have H2O. Well, first we have a secondary alkyl halide, so that could be either one. But we have H2O, which is a neutral nucleophile. It's a polar protic solvent, so this is preferring SN1 mechanism. Now there's a catch here. So we could be tempted to write just the substitution. Now it would scramble stereochemistry, so you can either write a squiggly line or just a straight line. We'd be tempted to write this product here. However, this is not the product that is going to be the major product. If we look at the mechanism of this, we see that our intermediate is going to be this carbocation here, but we have a hydride right next to it that can shift and create a tertiary carbocation. So we've moved the hydride here, and we have a tertiary carbocation. Because we can do that shift and form a more stable carbocation, we're going to form, the substitution is going to occur at this tertiary position instead of this secondary position. So our actual product would be substitution at the tertiary position, not the secondary alcohol. So you'd end up with the tertiary alcohol. And this would be, as we confirmed, this is an SN1 type mechanism. All right, let's examine this next one. We have a tertiary center that almost always tells us that practically tells us exactly that it's going to be an SN1 mechanism. Just to confirm, neutral nucleophile, polar protic solvent, we are definitely an SN1 type mechanism. So we're going to do substitution with this group. This ends up being the acetate. This is acetic acid, so we have an acetate substitution with bromide. So we maintain the carbon chain. We'll still have tertiary center, and we'll bond via the O. Remember, this O is what's doing the nucleophilic attack. That's going to attack here. So we have bonding through the O to make this acetate ester. All right, this last one, we saw before, we have a secondary alkyl halide. We have a good nucleophile, so we're primed for either SN1 or SN2, so we have to look at the solvent. We look, methanol is a polar protic solvent, so we will instead prefer an SN1 type mechanism for this. So the product is almost exactly the same, except we scramble stereochemistry at the stereocenter. So we lose the stereochemistry. So we can either write that like that with a straight line, or to indicate a racemic mixture, we can write it with a squiggly line. Both of these answers would be correct. And since it's an SN1 mechanism, we lose the stereochemistry. Whereas we saw in the last example with this type of reaction, we had inverted stereochemistry because it was an SN2 mechanism, whereas SN1 scrambles the stereochemistry.